Okay. Might go out of view, but that's fine. We will hear Zoom if they speak from somewhere else, right?
They will hear what?
Will we hear people from Zoom from somewhere else? Because I
think they cannot.
No,
they cannot talk. Oh, okay.
You can type
Okay.
questions. So
Okay.
That's my purpose.
That's fine. That's okay. That's cool. Yeah. I was just asking to see if I should turn on my speakers. Probably not.
Yeah, yes.
Yeah. Okay, this one is not gonna work for me today, so I'm just gonna use. I have to bend and click the arrow keys, but it's fine.
Hopefully for Wednesday we can get it to work. So but this thing,
That's mine.
You brought it, right?
Yeah,
Okay.
it's mine. I failed to set it up.
You can start anytime that you feel comfortable.
Yeah, I'm ready. Ready to start. No, let's wait 2 minutes.
Sure, yeah, no problem. Sure. Did you receive the information for Wednesday's talk?
Yeah.
Perfect.
Yeah.
Do you have
At the same time, right?
Yes.
No, I don't have any questions. It's gonna be something like this.
Yeah. Different room because this one was booked.
Yeah.
But yeah, something like that.
So thank you, everyone, both here and in Zoom. We have the pleasure of having Ataberk Olgun with us today. And he's going to present us the plethora of work that he has been doing. Tell his advisor it's time for him to get his PhD. And I think if he was at UPC, he would have 5 times the PhD by now. His talk is, the title is Experimentally Understanding and Efficiently Mitigating DRAM Read Disturbance. And he's a 4th-year PhD student in the Safari Research Group at ETH Zurich. So he's a student of Professor Onur Mutlu. And his broad research interests include designing secure, high-performance, and energy-efficient memory systems. His current research focuses on deeply understanding and efficiently mitigating the vulnerabilities caused by technology scaling in modern systems. His graduate work has been recognized with several honors, including induction into the HPCA Hall of Fame. I don't think at UPC we have anyone student who has been inducted to the Hall of Fame. It means that they have at least 8 papers in HPCA. So pleasure to have you here. So floor is yours.
Thank you very much, Osman, for the kind introduction. The pleasure is mine. I'm very excited to actually present my work to a brilliant group of researchers in BSc, and I'll get started. So this is the title of the talk. Osman already introduced it. I'll skip a brief self-introduction, because Osman already covered these points as well. I'm broadly interested in computer architecture, but I've been mainly doing research in memory systems, robustness specifically. So today's talk will be about memory isolation, or lack thereof, in our systems. Memory isolation is a key property for system robustness. That means basically a memory access should not have unintended side effects on data stored in other addresses. If we do not satisfy the memory isolation property in our systems, this can lead to data loss, corruption. It can compromise application correctness, leak private information. It can allow malicious actors to take over our computers. And mitigating or satisfying memory isolation in today's systems is difficult because we use DRAM everywhere, and DRAM is fundamentally prone to redisturbance errors. And these errors can be used to break memory isolation. That's what I just said. This picture here depicts tightly packed rows of DRAM cells, and you need to drive a word line with a very high voltage value to access this row of DRAM cells. Now, if you repeatedly access a DRAM row many times, you'll induce bit flips in neighboring cells. And we call the repeatedly activated row the aggressor row, and the rows with bit flips victim rows. This phenomenon is widespread, and it affects almost all real DRAM chips you can buy today. And nothing changed with respect to that in the last 11 years. And one way to understand the underlying mechanisms that lead to these bit flips is to look at DRAM charge leakage. Each DRAM cell encodes data in fundamentally leaky capacitors. And this is a simplified diagram of a cell where this capacitor in red stores data, and the access transistor determines if the cell is being accessed. And there are a number of leakage paths by which charge can enter or exit the cell. Now, the important thing to note is that stored data can be corrupted if too much charge leaks. So here we have a simplified diagram of the capacitor voltage over time. We see that the voltage decreases over time in an exponential decay. And there's a threshold, which we call Vmin, under which we can no longer guarantee that the cell will store the data correctly. Now, as long as the cell's voltage remains above this line, we're fine. This is a retention success. But if the voltage drops below that threshold, we consider this a failure. And in order to prevent such failures, we periodically refresh our DRAM cells. Now, that's the basic idea of DRAM charge leakage. Now, let's look at this in the context of a RowHammer attack or RowHammer access pattern. If we issue enough activations to a nearby row, we can accelerate this charge leakage to a point of failure. So subsequent refresh commands that start after this point in time will see the incorrect value in the cell and store the incorrect data back to the cell. This paper showed that the RowHammer bit flips were sort of widespread across many DRAM modules in 2014. And then researchers from Google Project Zero showed that you can use these bit flips to gain write access to your own process's page table. And from there on, you can gain read-write access to whole physical memory. And since then, a plethora of exploits emerged. Researchers demonstrated RowHammer attacks in many different platforms over many different mediums. You can do this over network. All you need is a means to access physical memory or main memory. In FPGA-based systems, you can also use this as a side channel attack, not just to take over systems. You can leak secret data as well without being noticed per se. And you can use these bit flips to significantly degrade the outputs of neural networks as well. There are many papers about this topic, especially. You can find that researchers induce targeted bit flips in certain locations in your neural network application's memory, and you can significantly degrade performance of that application. You can see, I mean, you can find the exact numbers in the papers I refer you to here. There's one more interesting aspect. This one work in particular shows that error correcting codes typically used to provide error tolerance in many security critical systems, let's say, are not as effective as previously thought against read disturbance bit flips, because you can induce bit flips that go beyond the correction capabilities of mainstream error correcting codes. And solving redisturbance bit flips with error correcting codes tend to be very expensive. So then DRAM manufacturers implemented some undisclosed RowHammer mitigation techniques for DDR4, and claimed that they have solved RowHammer, but then this one reverse engineered these techniques and came up with specialized access patterns that bypass these mitigations. And then there's an overview paper from my advisor that covers RowHammer updates until around 2020. And then we recently wrote a newer paper that covers the development between 2020 and 2023. So if you're interested, I'll refer you to these works. Even after that, many other works appeared. I'll quickly skim through these. There was this one in Unix security 2 years ago, in particular, just last year. There was one paper that showed bit flips in one of the newest DDR5 modules. This was just one bit flip, but it was still interesting to see. And then more defense mechanisms appeared in Micro 2024. And meanwhile, in April 2024, the JEDEC, Joint Electron Devices, I don't know the exact meaning of the word, but this is a basically console that many companies come together to make decisions about DRAM standards. And they finally standardized a defense mechanism. So this is the first promising update a decade after the discovery of RowHammer that's called per row activation counting in DRAM. We analyzed the security guarantees of this technique. Long story short, it can provide security guarantees against RowHammer as very low thresholds where only like tens of activations would induce a bit flip. But it can hog DRAM throughput to a great extent and cause extensive slowdowns. And you can find more details about that in this paper. We also recently published another paper that builds on the this PRAC mechanism and improves it so that you wouldn't see those huge overheads. And I'll be happy to talk about these if you have questions. But I'll just show this. There was a RowHammer session in ESCA 2 months ago. So this, I think there will be more research in this area because redisturbed bit flips happen in more DRAM cells with fewer activations as DRAM technology scales to smaller sizes. And we see more than 10x reduction in redisturbance threshold between chips manufactured 7 years apart. That's to say that basically DRAM chips become more vulnerable to redisturbance as we scale technology to meet our needs. So let me summarize what I've covered so far. Memory reliability is reducing and we see new security vulnerabilities. These are hard to defend against, and RowHammer is one good example of these. And I think the bad news is it's getting worse. The good news is that it gives this opportunity to develop new techniques and understand this phenomena better. And the rest of today's talk will be about developing our understanding of these vulnerabilities and efficiently defending our systems against them. So I'll start with I'll continue with variable read disturbance. This is an experimental analysis of temporal variation in DRAM read disturbance. This is a typical DRAM-based computing system with a CPU and a DRAM module with multiple chips. Each bank contains each chip contains multiple banks. Inside banks, we have what we call subarrays. And within subarrays, you have DRAM cells laid out onto a two-dimensional array of rows and columns, or word lines and bit lines. And these cells are connected to a row buffer via these bit lines. So to access a data in a row, you need to activate the row. And basically, if you repeatedly activate this row many times, you can get redisturbance bit flips. They have significant implications because they break memory isolation, as we discussed. So I'm going to go relatively quickly over these. There's also one more thing. There's RowPress. RowPress induces bit flips by keeping the rows open for a very long time instead of repeatedly activating the row many times. And I'll talk about this more, but we have seen in extreme cases with a single DRAM row activation, you can induce bit flips if you keep the row open for long enough. So prior works propose many different techniques to mitigate redisturbance bit flips. They have basically, these are all valuable, I think, because they come with different reliability, performance, energy area trade-offs. But a common operation pattern across these techniques is that they take an action before a bit flip manifests in a victim row. And to do so, they must accurately quantify the amount of read disturbance a row can withstand. And this is typically quantified by time-intensive testing for read disturbance failures. The read disturbance threshold, or RDT for short, is the metric that quantifies the amount of disturbance that your row can withstand. And this is expressed in terms of the number of activations. Now I'll try to illustrate why it's important to accurately identify that value. So the x-axis shows increasing RDT values in arbitrary units. The y-axis shows you the performance energy overheads of your mitigations, again in arbitrary units. So this is a curve you would expect to see as RDT becomes smaller. Redisturbance solutions induce more performance overhead because they need to perform more mitigative actions like victim row refresh operations. If you have this ground truth RDT value for the row, you want to configure your defense mechanism with that exact value, because if you configure it with a higher value, you cannot mitigate bit flips. You're no longer secure. If you configure it with a very low value, if you're overly conservative, you incur unnecessary performance overheads. So in summary, we must accurately identify the threshold value to securely prevent bit flips at low overhead. And our work tries to answer a key question about redisturbance that's not been answered before. So how accurately and efficiently can you measure the redisturbance threshold of each DRAM row? For this, we record more than 100 million redisturbance threshold measurements across many rows and many chips. And we find that the threshold of a DRAM row varies significantly and unpredictably over time. And the largest observed RDT for a DRAM row can be 3.5 times the smallest observed for the same row. And this very small value can appear after as many as 94,000 measurements. And we call this new phenomenon variable read disturbance. Variable read disturbance has implications for system security and robustness because you cannot identify the read disturbance threshold of a row quickly and accurately. And we evaluate using guard bands for the read disturbance threshold and error correcting codes as a solution for VRD-induced bit flips. And given our limited bit flip data set, we find that relatively large guard bands and ECC could prevent VRD-induced bit flips, but they come at a significant performance cost. And we think that more data and analyses are needed to make more definitive conclusions here. And our results call for future work on understanding and efficiently mitigating the variable read disturbance phenomenon. So I'll go into details now. This is the outline for the rest of the talk. I've already motivated it a little, but I'll just make sure it's substantial. So reducing read disturbance thresholds or worsening read disturbance causes existing mitigations to become more aggressive, and in turn they induce higher overheads. Moreover, prior works assume that the ground truth read disturbance value can be identified, but in our work we challenge this assumption, and we see that no prior work studies the temporal variation of DRAM read disturbance and its implications for future solutions. So our goal is twofold. We would like to answer two research questions. Does the read disturbance threshold change over time? And if so, how reliably can we measure it? And the second goal is that we would like to analyze the implications of variable or temporal variation of read disturbance for read disturbance solutions. To achieve these goals, we experimentally characterize DRAM chips using this infrastructure, the DRAM Bender testing infrastructure, to test DDR4 modules. This provides us with fine-grained control over DRAM commands, including timing parameters and temperature. And this is another version of the same infrastructure that we use to test high bandwidth memory chips. So these are the chips we tested. We span various die density, die revision, and chip organization configurations from 3 major manufacturers. And all of this is just to say that we carefully reuse the existing testing methodology as done by prior work to prevent sources of interference. This is not very important at this point. But the important thing is this bottom figure depicts one hammer operation. So if you open and close the 2 neighbors of a victim row, that constitutes one hammer in our case. So I'll describe our major results for VRD. This is the major takeaway. the redisturbance threshold of a row changes randomly and unpredictably over time, and this makes accurately identifying the redisturbance threshold very challenging. So I'll show you pictorially what this means. We'll plot the redisturbance threshold values observed across many threshold measurements or samples or observations for one DRAM row. And this is one example point in the plot describing one measurement that yields a redisturbance threshold of 37,000-ish hammers. So this is across 5 measurements. This is across 1,000. And I want to expand the x-axis further and still make sense out of the plot. So I'll compress the series into this, this form where the circle shows the average across 1,000 measurements. Maximum and minimum are the bars. And this is the redisturbance threshold across 100,000 measurements for one DRAM row. Here we observe that for this series of measurements, the minimum RDT, redisturbance threshold, appears at around 17,000 measurements. And I think this is a key result that demonstrates the variable redisturbance phenomenon. We also investigate the distribution of these observed redisturbance threshold values. This is a histogram of RDT values where a bar's height basically indicates the number of measurements that yield what you see on the x-axis. We observe that the redisturbance threshold of a row takes various different values across 100,000 measurements. And this is the data for 6 other chips. And this observation is consistent across all tested chips. Now, we test more, but I have to refer you to our paper for more results because they wouldn't nicely fit in that previous slide. We also analyze the predictability of the next redisturbance threshold value given past redisturbance threshold measurements. And we find that this is likely unpredictable. So I'll explain what that means. We find that these histograms well resemble prominent random probability distributions. That's one hint that makes us think that it's unpredictable. And the second is that we use the autocorrelation function to try and identify repeating patterns in this series of redisturbance threshold measurements, and we cannot identify any repeating patterns. For more details on our methodology, I'll again have to refer you to the paper. Now we'll take an in-depth look at VRD in many DRAM rows by sweeping various test parameters. We use 4 data patterns, 3 temperature levels, and 3 different aggressor row on-time values to investigate RowPress. We test many rows in total across all chips and measure the redisturbance threshold 1,000 times for each row. We test 1,000 times because of time constraints. The experiments would take too long if we didn't. But it's good to think about what you would expect to see if we did this testing for maybe more than 1 million times. Now, these are the 3 key takeaways from this in-depth analysis. First, we see that all tested rows exhibit some degree of variable redisturbance. So here we show the coefficient of variation in the distribution of 1,000 redisturbance threshold measurements for each tested row. I'll explain what this means. So this circled tiny dot stands for the DRAM row with the smallest y-axis value. Another way to look at that is basically that this row's redisturbance threshold values are very close to each other. And we show that here we show the rows sorted and increasing coefficient of variation on the x-axis. And this is what we see. No row has basically 0 variation in its measurements. And we highlight 2 points in this plot, the median row and the row with the greatest variance in its RDT distribution. These are basically distributions expanded on the x-axis over measurements here for those 2 rows. The one on the left is the median row. The one on the right is the one with the greatest degree of variation. So for the median row, we see that the maximum redisturbance threshold value is 1.2 times the minimum. And for the other one, we see that it can reach a very high factor of 3.5x. Now I'll move on to the second takeaway, which is that relatively few measurements are unlikely to yield the minimum redisturbance threshold for a row. So we're trying to answer this question: how likely is it for us to find the minimum observed redisturbance threshold across 1,000 measurements with only n measurements where n is basically smaller than 1000. We use Monte Carlo simulations and plot the probability of identifying the minimum value over basically varying n for all tested rows. N equals 1 measurement has a very low probability of identifying the minimum RDT across 1000 measurements. It's only 0.2%. And we observe that the probability increases with n, which is what we would expect to see. It goes up to 75% for the median row for 500, n equals 500 measurements, but it does not reach 100%. So I have more detailed results that I'll skip in the interest of time. We're trying to also quantify basically with n smaller than 1000 measurements, how close you would expect to get to the minimum value. So this is a bit too detailed, but I'll make the most important conclusion here. I think is this one. The minimum redistribution threshold is significantly smaller than the one we expect to be found with n equals 1 measurement. So if you randomly pick one measurement out of those 1000 measurements, you end up with something 1.9 times greater than the absolute minimum across those 1000 measurements. And again, with increasing n, you expect to find the redistribution threshold value that's closer to the minimum. We also look at the effect of data parents, temperature, and aggressor on time, and you can find detailed analyses in the paper. There's nothing too surprising to describe in this relatively short talk time frame, so I'm not going to cover them, but please have a look at the paper if you're interested. Now, these observations have implications for system security and robustness. The security guarantees provided by redisturbance solutions rely on an accurately identified threshold, and we show that this is difficult to identify. And we evaluate a short-term solution that is combining a guard band for the redisturbance threshold with error-correcting codes. And given our limited data set, we show that this solution could prevent VRD-induced bit flips, but at some performance cost. And we think that there should be future work on online redisturbance profiling and runtime configurable redisturbance mechanisms. And so I'll stress this caveat. The results I summarized in the previous slide are based on a limited number of measurements. It's just 1000 measurements. It's always, I think, good to think about what more measurements could have yielded in this study. But we didn't have infinite time, so we couldn't do that. So that was a summary. We will do a slightly deeper dive. So the variation in the redisturbance threshold can reach 3.5 times, and it may not be bounded. And it's affected by many parameters, and comprehensive redisturbance threshold testing is time intensive. We find that measuring the threshold of each row in a bank only once can take 39 minutes. So this is definitely much longer than what standard industrial IC testing times are, which is in the order of minutes these days. In fact, we show that comprehensive redisturbance threshold testing can take tens of hours if you want to measure the redisturbance threshold multiple times. And more details are in the paper. So because it's so time consuming to comprehensively test the redisturbance threshold, a system designer might measure it a few times, take the minimum across those few measurements, and then apply a guard band with the hope of covering all possible bit flips. I don't have a lot of time to explain this plot, but we observe that a large guard band alone does not guarantee that the minimum redisturbance threshold is always identified. And we conclude that guard bands alone are not effective, likely not effective. And large guard bands can also induce significant performance overhead. Thereby, we don't recommend relying solely on guard bands. Now, with error correcting codes, it becomes a bit different. So this plot shows you a histogram of the number of unique bit flips in a row when we use a 10% redisturbance threshold guard band. That's to say, basically, if you identify the minimum threshold for a row with few rounds of testing, and then let's say that minimum was 1000, you apply a 10% guard band, so you use a redisturbance threshold of 900. Now we're testing for bit flips at 900 activations. We still see that up to 5 bitflips can appear in a row if you do your testing that way. So this suggests that widely used ECC schemes combined with 10% guard band for RDT is likely unsafe, depending on how these bitflips are located, because most techniques that we use today cannot correct more than 2 bitflips in a code word. However, it's not all doom and gloom, and guard bands greater than or equal to 20% yield only one unique bitflip in a row. And the bitflip patterns that we observe can be basically can be prevented with this much guard band combined with the widely used ECC schemes. But I think we need more analyses, likely following a much larger scale study to make definitive conclusions about the effectiveness of guard bands in ECC. So there are many more things in the paper that I cannot talk about now. In the interest of time, I'll refer you to the paper again. And I'll just say that in this work, we demonstrated variable redisturbance, showing that the redisturbance of threshold of a row changes unpredictably over time. And I've talked to you about the degree of the variation and the implications for future solutions. So we have an extended version of this paper on arXiv, and that's it for VRD. I'll stop to take questions momentarily if you have any. Otherwise, I'll continue.
I think there's a question from John McCalkin. For the case of ECC memory, what is the probability that a RowHammer attack will generate an undetected error without first generating one or more detected errors?
That's a good question, and from the top of my head, I cannot answer this. But I think with the there are many papers that show let's say the number of bitflips you get with certain number of hammers. So this can be done. This sort of analysis can be done, although not just right now. I'll be happy to talk offline with whoever asked this question. But with very high hammer counts, if you don't have any mitigations, maybe I can show you some data here, actually, just very quickly. Here. So if you don't have protection, meaning some redisturbance solutions, and this is again for one particular chip, this is for HBM2 chips, one of the HBM2 chips, you can have up to 247 bit flips in a row of 8,000 bits. So that's a relatively high bit error rate if you think about it. And these error rates could very well exceed the correction capabilities of mainstream ECC techniques relatively easily, I would say. But with adequate protection, and if you set your guard bands correctly, and then that's a different story, and that's not, I think that's a research question, I would say. Yeah. Okay. So if not, okay, I need to go through 200 more slides. I think I know. So prior to VRD, we also looked at redisturbance in detail in high bandwidth memory chips. We knew that many DRAM chips of various forms were subject to redisturbance, and we were curious to see how it looked like in high bandwidth memory. These chips are extensively used in important system infrastructures of today. Several popular machine learning applications rely on high bandwidth memory today. A typical high bandwidth memory system looks like this. It consists of a compute chip and multiple HBM2 chips, or sorry, high bandwidth memory chips. All of these are integrated into a single package to form the system. And this is a different view of the same system. I won't explain this in detail. I'll just say that we have many 3D stacked DRAM dies in a high bandwidth memory chip. That's kind of what makes it, different from those other planar DRAM technologies. If you look inside the channel, you'll see the same subarray structure that I showed earlier. We also use the DRAM vendor testing infrastructure in this work. We adapted it to work with high bandwidth memory chips for the first time for this work, and its adaptation is open sourced at the same link. This is, again, an expanded photo of one of our testing setups. We use the FPGA board here that has an high bandwidth memory chip. We control the heating pad here and the cooling fan here using the Arduino temperature controller to keep the testing setup's temperature stable. And again, this gives us fine-grained control over DRAM commands and so on. So I'll actually take this opportunity to expand on DRAM and talk a bit about also why I'm here doing a project. So I'll talk about this infrastructure, DRAM vendor. It's an extensible and versatile FPGA-based infrastructure to easily test state-of-the-art DRAM chips. I'll just motivate why we have this. So many different factors affect DRAM reliability and latency characteristics, and these cannot be properly modeled easily. So therefore, we need to perform experimental studies using real DRAM chips. That's the motivation for DRAM vendor. There are open source DRAM testing infrastructures that would allow us to do these experiments, but they have several limitations that made them difficult to use as flexible, accessible, and extensible platforms when we pushed out DRAM vendor. Its goals, DRAM vendor's goals, are to overcome the limitations of prior work. So it's designed to give the user the ability to test any DRAM command sequence with any timing parameters. And it's very easy to conduct experiments, I would say, using DRAM vendor because we provide a simple C++ API. Now we also have a Python wrapper for that API and many code examples you can build on if you wanted to test DRAM chips. We support, I think, this is outdated, 6 FPGA-based prototypes out of the box in our GitHub repo. And in the paper we published on DRAM vendor, we did 3 case studies to showcase, DRAM vendor's flexibility in DRAM testing. There are more details in the paper. DRAM vendor has enabled a lot of research, which I am kind of proud of. I talked about this one. I will talk more about this redisturbance and high bandwidth memory paper. There's also another highlight I'd like to make, that's RowPress. These are other papers that we wrote using data generated with DRAM vendor. And it also helped other researchers do their own work. So I'll highlight RowPress. In RowPress, we found that keeping a DRAM row open for a very long time is also enough to induce bitflips, and they don't require many activations. That's what makes RowPress sort of unique. Only one activation can be enough in some cases, which is very extreme. But if you look at these timing diagrams, this shows the difference between RowHammer and RowPress access patterns very nicely. So these are based on average numbers across many tested DRAM chips. So if you keep a row open for 36 nanoseconds, that's the minimum you could for DDR4 chips, you need 47,000 activations. If you keep a row open for 7.8 microseconds, which is within the spec, you can do this. You need only 5,000 activations. And this makes it more difficult to mitigate redisturbance bitflips because with lower thresholds, your defense mechanism is going to induce more overhead. We have more results in the RowPress paper, and this is completely open source and artifact evaluated as well. So I'll talk a little bit about what I am doing here for 2 weeks. So we wanted to enable support for DRAM vendor in the MEEP cluster for some time now at BSC. And this has a potential to enable large-scale and flexible high-bandwidth memory DRAM testing because in the MEEP cluster, we have a lot of these boards, U55C boards, which come with HBM2 chips. And DRAM vendor now supports U55C boards. And thanks to, I think, many people involved, but I guess specifically Behzad Salami, I'm working with Behzad, who's also hosting my visit and has been collaborating with us to make this happen. So I hope to gather some data and present some results actually in my other talk on Wednesday. So just a little bit about Severo Ochoa. This is a physician and biochemist. He is a physician and a biochemist. He won the Nobel Prize in 1959 for the discovery of the mechanisms in the biological synthesis of, I won't be able to pronounce that, DNA. So basically he synthesized RNA outside the cell for the first time, which I think is very cool. And if you're interested, he delivered a very humble Nobel Prize acceptance speech. You can find at this link below. Early on in his career, he had to leave Spain to focus on his research. And the Severo Ochoa Mobility Grant enables researchers to participate in cross-institutional research. And I'm honored to be one of the recipients of this grant. So that's it for DRAM Bender, actually. This is the first publicly available DDR4 and HBM2 now characterization infrastructure. It enables, I think, a lot of good DRAM testing, insightful, enables delivering insightful results. It's flexible and easy to use, and we hope that it will continue to enable many new studies and the design of future memory systems. So that's the paper we published on DRAM Bender and a lot of other resources if you're interested in working with DRAM Bender. So I'll come back to the HBM2 study. Again, this is about the testing methodology that I already described, so I'm going to skip this. You have two metrics here. The bit error rate is the fraction of DRAM cells in a row that experience a bit flip after 256,000 hammers. That's also within spec. And the second one is the minimum hammer count needed to induce the first bit flip. I will refer to this as the disturbance threshold because I think that's easier to relate to at this point. I'll show you just a few results. I'll show you how bit error rate is distributed across different 3D stacked channels. The y-axis shows you the number of, or the fraction of cells that have errors. And different boxes here show you the data from different 3D stacked channels. The observations we make here are the simplest one is that there are bit flips in every channel. And the bit error rate varies across channels. And an interesting thing is we find that groups of two channels, like the ones I highlight with the same color here, have similar bit error rate profiles, and we attribute this to two different channels being placed on the same die, maybe in the HBM2 chips for testing. So there are like four layers, and each layer has two channels of DRAM. This is a larger version of the figure that shows more data patterns. We make the same observations, and we see up to 247 bit flips in a row of 8,000 bits. Again, more data patterns. So I'm going to skip these, go over them very, very quickly. Again, I won't bore you with too many details. I will show a picture about the second takeaway that says DRAM rows near the end and in the middle of a bank are more resilient to the disturbance, basically. In this plot, we have on the x-axis increasing row addresses. So if you go right, you get to the end of the bank. Here we see that the bit error rate is substantially smaller in this middle and the last subarray. And within a subarray, the bit error rate increases and then decreases as you go towards the end of the subarray. We have hypotheses that explain these behaviors in the paper. If you're interested, I'll unfortunately have to refer you to the paper in the interest of time. We also look at the redisturbance threshold. We see that the redisturbance threshold can be as low as 14,000-ish, which means that you can get a bit flip in around 1.3 milliseconds of hammering. And I'll leave you with that much. So I have more interesting results about RowPress, but I won't cover them in detail. I'll just say that as you increase the row on time, as you keep a row open for longer, you get more bit flips, and you get the bit flips with fewer activations. And I'll share the slides with you. So if you're interested, you can take a look at these. These have implications that I'll just briefly summarize as, if you can identify the most vulnerable channel, that's a good thing for defenses. That's a bad thing for defenses as well, because the attackers can also concentrate, let's say, their testing efforts in the channels that yield the most, that turn out to be the most vulnerable channels. But as a defense mechanism designer, you can also allocate your resources to defend these channels more and defend other channels less. We also uncovered a what's called an on-die RowHammer mitigation mechanism that was not described in the standard specification using the key idea is basically use data retention failures as a side channel to detect when a row is refreshed by a RowHammer mitigation mechanism. So these are details that I won't be able to cover again, unfortunately, but the key idea is, or the key takeaway is that there are undisclosed mitigation mechanisms implemented in the HBM2 chips we tested, and we can find a specialized access pattern that bypasses these mitigations and induce bit flips. And this is basically showing you a combination of test parameters that we swept with the mitigations enabled, with the DRAM being refreshed, you still get RowHammer bit errors, RowHammer bit flips. And this is what I wanted to show. So there are more things in the paper that I won't cover. I will basically just say that this was the first detailed experimental characterization of disturbance and modern high-band memory chips, and I'm hoping we can expand on this with the infrastructure in BSC, and we can uncover many more new behavior about DRAM read disturbance as well. Yeah, so that's it for the high bandwidth memory study. I'll switch gears and move on to defenses now with only 13 minutes left, but I hope maybe we can stick around for maybe 10 more minutes. Yeah. This is now Abacus. This is all bank activation counters for scalable and low overhead RowHammer mitigation. The RowHammer phenomenon is getting worse. We can induce bit flips with around 100 times fewer hammers compared to 10 years ago. You know this already. There are multiple ways to mitigate RowHammer bit flips, and we will focus on preventive refresh-based ones because they tend to make more efficient use of resources and induce smaller performance and energy overheads. The idea of preventive refresh is to refresh a victim row before bit flips manifest in them. Doing so kind of resets the disturbance effect. So you have another, budget of read disturbance threshold activations until you get to the bit flip. But doing this requires what's called aggressor row activation count tracking. And this gives us a way of determining when to refresh a victim row. We find that no existing prevention mechanisms, disturbance solutions prevent RowHammer bit flips at both low area, performance, and energy costs. And our goal is to enable that mechanism, basically. And our focus is preventing bit flips at very low RowHammer thresholds, for example, where 125 activations could induce a bit flip, which is not what we have seen yet experimentally. So to that end, we develop Abacus. Its key idea is based on this observation that your CPU tends to make memory accesses in a way that I'll show you. I'll animate this and then explain my reasoning. So your accesses touch the same row address in different banks at around the same time. The reason for this is twofold. So the first one is the intrinsic spatial locality in memory accesses. A program usually accesses neighboring cache blocks at around the same time. And you can think of a prominent access pattern, like if you stream through an array and in some code, you're touching neighboring cache blocks. And the second is modern physical address to DRAM address mappings place neighboring cache blocks into different banks, but in the same row. And they do this to leverage bank level parallelism and extract the most out of DRAM throughput possible. And to further motivate Abacus, we also empirically support this observation. And we investigate workload access patterns and show how well DRAM rows obey this observation. You can find the details in the paper. Unfortunately, I can't cover this. I'll talk a bit about existing solutions. There's an important problem of existing redisturbance solutions that are counter-based, that use counters to, figure out how many times a row is activated. The thing is, there are many banks in a DRAM chip, and the number of banks, and thereby the number of activation counters, increase with DRAM generations as we try to scale the density. We have seen that sibling rows, which is, the same row across different banks. Those are the sibling rows. Have similar activation counts, and our key idea is to use one counter for all those sibling rows and reduce the number of counters by a factor of the number of banks. That's the basic idea. I won't touch on the details unless you have questions. We can talk. I'll move on to our evaluation of Abacus. We use a cycle level memory system simulator called RAMulator, configured in this way. Again, this is for your reference and I won't cover it. We compare Abacus to 4 state-of-the-art mitigations: Graphene, Hydra, Rega, and Para. Graphene is the highest performance mechanism. Hydra is the Para is the lowest area overhead mechanism, and Hydra and Rega provide interesting trade-offs between system performance and area cost. We simulate 62 single and 8-core multi-programmed workloads from these major benchmark suites. We execute memory traces. So this is the system throughput on y-axis across all single core workloads for the RowHammer threshold values that we display on the x-axis. So the higher the bar, the better your performance. These are this mitigation mechanism induces some overhead that's relatively small. And this is the energy overhead. Here, a smaller value is better. From these plots, we conclude that Abacus prevents bitflips with very small performance and energy overheads compared to a baseline system that does not have any mitigation. This is 8-core multi-programmed performance comparison against other defense mechanisms, state-of-the-art defense mechanisms. So I'll say that Abacus outperforms Hydra and Para at all RowHammer thresholds, but it incurs a small performance overhead over Graphene. This is due to Abacus's unnecessary preventive refresh operations because it has a low-cost aggressor row activation tracking scheme. Basically, you're using one counter to keep track of the activation counts of many rows in all banks. So that can be up to 32 rows in 32 banks. If only one of those rows are activated repeatedly, you still have to refresh all the rows across all banks when that activation count reaches the threshold. That's where the overheads are coming from. This is the same plot for DRAM energy. Abacus consumes less energy than Hydra, Rega, and Para for thresholds smaller than 1000. And it performs similar to Graphene in terms of energy. We also analyze Abacus's area overhead. To summarize, it induces much less area overhead than Graphene, and it has somewhere close to Hydra's overhead for a very low RowHammer threshold. We exclude Rega and Para from these analyses because they don't incur processor chip area overheads. So there are more in the paper that I couldn't cover. Again, interesting things. I'll need to move on to the next paper because I really want to talk about self-managing DRAM. So I'll summarize Abacus. Based on the key observation that many workloads access the same row address in different banks at around the same time, we develop Abacus, which uses one counter to track the activation count of many rows with the same row address across all DRAM banks. And we show that this induces very small performance and energy overheads at very low RowHammer thresholds. So again, an extended version of our conference publication is available on archive. And this is also open source and completely open source and artifact evaluated. Okay, that's it for Abacus. Maybe I stop for 5 seconds if there are questions. Yes.
Vincent, thank you for your great talk.
Yeah, thank you.
Based on your talk, I understood that there are several features with varying behavior, and a common approach should be a machine learning approach to predicting and mitigating these faults. Okay, these bitflips. Have you used them? I want to know which feature has a dominant part, the dominant effect.
This is a very good question. I think it's almost a research question still at this point, because most work I think has been recently about mitigating RowHammer bitflips. So that involves counting usually, or some probabilistic mechanism. You throw a dice, and then if it has a certain value, you decide to refresh something. But there's not a lot of work trying to understand what exactly the redisturbance threshold for a row should be, and what we know that it depends on many different test parameters like temperature, data patterns that you use, location, time, but there's no holistic mechanism or methodology yet that you can use to actually determine with some confidence what it should be. And machine learning could be one, I think, great use case. I mean, one great use case for machine learning could be this problem. Yeah.
Yeah, there was a question from Nizam Rahbani, also in a similar vein,
Yeah.
about the RDT. And you did maybe mention a bit about the different factors. Yeah, it says, can you please explain more about the reasons for the variability in RDT? Which ones are from like location, temperature?
Yeah.
So which ones are more, let's say, I guess the question is which ones are
Yeah.
dominant or yeah, if you've seen that. Kind of like a principal component analysis.
So I think the most important factor is the row on time. There you can see a clear relationship. If you keep the row open for longer, you will induce the bit with fewer activations. Temperature, data patterns, position of the cell are less dominant. Not, I wouldn't say dominant, but they have an effect. It's not as high as the row on time. For example, physical location tends to have again an unpredictable effect. I can refer this person to a paper. I don't know his name. I'm sorry, or her or his name. I can refer them to papers where we discuss the effects of different test parameters on redisturbance threshold. Temperature has an interesting effect where you can see bit flips in a certain temperature range in a cell, like let's say between 50 and 70 Celsius. But after you exceed 70 Celsius, you don't see that bit flip anymore, only within that range. There are cells that have this property. There are cells that don't have this property. Another thing is data patterns. Depending on which chip you're testing, some data patterns end up inducing almost like 2x more bit flips than others. So there's a lot of variability. But I think like no holistic study is out there yet that says, okay, this varies based on that and that and that. Let's figure out what the redisturbance threshold should be. That doesn't exist yet. I'll have one more paper I want to discuss. Maybe I'll quickly go over it. Yeah.
15 minutes.
Okay, that's good. There's a lot of time. So this is self-managing DRAM. It's a bit different than what we've covered. It can be used for RowHammer mitigations as well, but it's more general than that. I'll explain. So this is I'll start with a summary. Implementing new in-DRAM maintenance operations requires modifications to the DRAM interface and other system components. And this you can think of as, you know, a new RowHammer defense mechanism is a new in-DRAM maintenance operation. Modifying the DRAM interface is very challenging. It's an involved process that requires multiple years of effort by the JDEC committee. Our goal is to ease and accelerate the process of implementing new in-DRAM maintenance operations. And our key idea is to propose a simple change in the interface that allows the DRAM chip to reject memory accesses that target an under maintenance region. And this single change in the interface also allows designers to implement new mechanisms without any future changes to the system components and the DRAM interface. We implement 3 in-DRAM maintenance mechanisms in SMD to show that SMD is useful and versatile. And our evaluations show that SMD enables performance and energy efficient maintenance mechanisms at small area cost. And we open sourced all data and sources at this link that's visible at the bottom. So this is the outline. This is at a very high level how the DRAM interface looks like today. That you have the DRAM chip communicating with the memory controller over the DRAM interface, a DDRX interface. You send the DRAM commands over the command bus, and you exchange data between the chip and the memory controller. Using this interface, the memory controller orchestrates all DRAM operations. It sends commands to the DRAM chip to do so, and the DRAM chip executes all commands without any question. And thus, we say that today's DRAM interface is completely controlled by one side. And an important type of DRAM operations are those performed by maintenance mechanisms, because DRAM is subject to so many error modes, such as the ones we discussed. We need maintenance mechanisms to maintain data integrity, and one prominent example is refresh. Like another prominent example beyond RowHammer mitigation is refresh, where the controller periodically issues refresh commands to DRAM. As manufacturers scale storage densities, these error modes cause memory rates to increase. And the key is that continued DRAM process scaling will necessitate new maintenance mechanisms, and it has done so actually. And these are defined as part of the standard specifications where more than 300 companies are involved in. They define the DRAM standard and produce devices that obey the standard. And this standard poses a barrier to entry for new efficient maintenance mechanisms, because adding a new or modifying an existing mechanism will require modifying the DRAM specification. And the key reason for the barrier to entry is that this interface is rigidly defined. It's also not easy to release a new DRAM specification, because doing so requires a multi-year effort by the JEDEC committee. And introducing new maintenance operations therefore takes a long time. It's not necessarily that a new maintenance mechanism will take 5 years to develop. It's just that to standardize it, you need to go through a lot of time-taking processes. So for example, the recently released DDR5 standard introduces 3 maintenance techniques. I won't cover them in detail, but the point is, if new maintenance mechanisms could be more rapidly released, we could have seen these earlier in DDR4, for example. Now, the problem is, again, I'll just summarize, introducing new operations, new maintenance operations specifically, take a long time. And our goal is to ease and accelerate the process of implementing these maintenance mechanisms. So we have 2 operation classifications, DRAM operation classifications, what we call access operations and maintenance operations. The access operations are performed by the memory controller to serve memory requests. And if you think about it, this uses information available only to the memory controller, such as the load address or the stored data. So if you think about the other component as DRAM. Whereas maintenance operations, we do to maintain data integrity, but this typically does not use information outside the DRAM chip. So all information you have is available to you as the DRAM chip. A key observation here is that then you can say that the DRAM chip has all the information, therefore it could maintain itself. And it should maintain itself, because first you can implement new maintenance mechanisms more easily, more rapidly, because doing so would not change the interface. And it enables DRAM manufacturers with some breathing room to perform architectural optimizations without exposing DRAM internal proprietary information to other parties involved in the JEDEC standard, the JEDEC committee. So our solution approach is to enable autonomous maintenance operations in DRAM. However, the DRAM interface today is too rigid to accommodate autonomous maintenance operations. In particular, DRAM interface is designed in a way that yields all control to the processor chip. And our goal is to make a simple change, a one-time change to the DRAM interface, and enable autonomous maintenance operations. So another way to look at this is we aim to give breathing room to DRAM by moving towards the right in this interface design scale. So to that end, we develop self-managing DRAM. This enables autonomous in-DRAM maintenance operations. The DRAM chip has full control over the maintenance operations, and you can this way add new maintenance operations to your DRAM chip and not modify the standard. One problem that this introduces, though, is that access operations can conflict with the maintenance operations. So you can access a region in the DRAM chip that's undergoing a maintenance, and you have to resolve this. Our solution to this problem is to make a simple change in the interface that allows the DRAM chip to reject some of the activate commands that target under maintenance regions. So in summary, we enable autonomous in DRAM maintenance operations with a simple change, and SMD divides the work nicely between the memory controller and the DRAM chip and enables you to add new operations without modifying the standard. So I'll walk you through SMD's design. We'll start with SMD bank organization. So this is a DRAM chip. It contains multiple banks. We've seen this already. We have many subarrays in a DRAM bank and many rows in each subarray. This is what a DRAM bank with SMD looks like. So we introduced the concept of lock regions. They define the granularity of a maintenance operation. So if you are doing refresh, you will do it in one lock region as the DRAM chip. We have the lock region bit vector that indicates the regions that are undergoing maintenance. This is just 1 bit per region. So this is as many as the number of subarrays in your chip. So it's very small. And we have what we call the lock controller that orchestrates this locking and releasing of regions. With support for SMD in a bank, your chip will lock a region before it starts doing maintenance operations in that region. Now we'll talk a bit about the locking mechanism very quickly. In summary, there are 4 steps. First, you lock the region that you want to do an operation on. If the memory controller wants to access the DRAM chip, it can access regions that are not locked. So there's a way for us to parallelize maintenance operations with access operations. But if the memory controller accesses a region that's undergoing maintenance, it receives a negative acknowledgement. And once you're done maintaining one region, you can release the lock. So with this substrate enabled in the DRAM chip, how do you control the SMD chip? All access operations look like they look today, basically work like they would today, except that some activate commands may get rejected. So the memory controller needs to retry these commands, and it can attempt to access other lock regions while waiting for one lock region to become released. So we have a proof in the we prove in the paper that the SMD chip and the memory controller they work together to ensure forward progress for every memory request. So no memory request gets negative acknowledged forever. I'm running out of time, so I'll quickly say that, explain how the memory controller deals with the rejection. So you send an activate command, receive a negative acknowledgement, and then you will at some point need to retry this activate command. We introduce a new timing parameter because the memory controller is used to working with timing parameters. There are already tens of those defined. This is called the retry interval. So after you receive a NAC, you won't be able to send another activate to this lock region for this much time. And then you can retry again. Or you can try accessing another lock region because if your workload is memory intensive enough, you will have other requests waiting in the queue that you could schedule to other lock regions that are not undergoing maintenance. This enables you to overlap the latency of maintenance with access and enables performance improvements. And we prove that this doesn't lead to resource starvation issues in the paper. So we implement various maintenance mechanisms in the paper and discuss many others that we couldn't implement and evaluate. I'll quickly go over these. I think one good example is refresh. So normally you would send 8,000-ish refresh commands in 64 milliseconds to DDR4 chips. But none of this needs to be sent with SMD. So you save energy in the bus because you don't send refresh commands. The bus is not occupied by refresh commands also. So that gives you more throughput. And you can access most of the chip that's not under maintenance. This gives you the performance benefits. So we evaluate, I'll talk a bit about the overhead of the alert 10, the negative acknowledgement signal. So today there's an alert 10 signal that already goes in this direction from the DRAM chip to the memory controller. You can repurpose that at no additional pin cost, or you can add a new pin, which comes at like 1.6% pin count overhead for a relatively modern processor chip. We also evaluate the DRAM chip modifications we need, and we show that it's not very large. So the memory controller also needs some modifications, but this is also, again, very small. We evaluate SMD using RAMulator, using the similar methodology to what we used in Abacus, and we evaluate many different system configurations. I'll just say that SMD provides 4.8 to 5.0% average speedup across different configurations. And the important thing is, if you get rid of refresh completely, so you have a DRAM chip, hypothetical DRAM chip that does not require any maintenance operations, SMD gives you 84% the benefits of that. We have results for multi-core, multi-programmed workloads. We have energy results. We show that SMD provides energy savings. And to summarize the performance and energy benefits, it's just that SMD gets you those that a no refresh hypothetical configuration would almost get, basically. And there are more details in the paper that I would have loved to cover. But let me summarize. So maybe I'll not summarize. I've talked about this already. I think our hope with SMD is that it enables practical adoption of innovative ideas in DRAM design and better ways of partitioning work between memory controllers and DRAM chips. And again, extended versions available on archive, and this is also open sourced. I think with that, let me just go over this slide once more. I hope that these points are now substantiated in your minds. I think RowHammer is still, like, read disturbance is becoming worse, and I still think we have a lot more to do. So with that, I'll end my talk. Thank you for sticking with me for an hour and 10 minutes. And I'll be happy to take more questions if there are any.
Thank you. Maybe we have time for a quick question or two before we come in for lunch. Any questions? Online or
No?
Everybody hungry?
Between people and lunch.
So for this, I mean, let me throw you one.
Yeah.
For the very nice work for the locking mechanism. So how do you bound the, I mean, forward progress is one side.
Yeah.
And for, let's say, like hard real-time systems, then you also have to have some kind of timing guarantees.
Yeah.
How are you pondering about that, or have you started going in that direction?
Yeah. So for very timing restricted systems, what you need is a more restricted interface definition, I think. We have one alternative implementation of SMD that basically bounds the region where this sort of knacking is allowed by the DRAM chip. So you would have like a maintenance region of, let's say, I'll just give random numbers, 5 microseconds. Every 5 microseconds, you are allowed as the DRAM chip to knack for 1 microseconds out of that 5 microseconds, let's say. So that gives you an upper bound. And then in the rest of that time window, the memory controller operates like it does today. That's one approach. So basically, JEDEC implemented the per row activation counters defense. It also operates similarly. What they did is, so right now, DDR5, if you want to enable that mechanism, you need to design your memory controller in a way that can deal with these negative acknowledgements. An alternative that JEDEC did is, if the alert 10 signal is raised, if the next signal is raised, you still have 180 nanoseconds to do your things. After that, you need to wait for this long. So that's another thing you could do. And the rest is up to, I think this basically would require probably collaboration between the DRAM manufacturer and the system designer to make sure some guarantees are met.
Thank you.
Yeah.
Yes, thank you very much.
Thank you.
You are going to be around for 2 more days.
Yes.
Right.
Yes.
Thanks.
Thank you.